Now we're going to start applying what we learned about probability. And what we're going to be introducing you to today, or in this module, is the application of probability to numbers. And this is how we use it quite often, and models. So models are an idealization, and it's a mathematical model, and so in mathematics there's right, wrong, exact, etc., and we bring that to bear in the real world, and that is where the art comes in how to apply these models to our benefit. What we're going to be talking about are what we call random variables. So we've developed this measure, this probability measure that we're applying to events, and now we're going to be applying it to numbers. And these numbers we call random variables. Random because we don't yet know exactly what value they take until we observe them. So the simplest one would be what we introduced when we started talking about data types, namely the dichotomous, or binary we said, which is also called Bernoulli variable. It's a variable that can take on one of two values. Let's call them 0, 1. We could call them 1, 2. We could call them anything we want, but let's just, for the sake of definiteness, call it 0, 1. So our variable x can take on the values 0 or 1, and we are going to be describing this variable probabilistically by stating what is the probability that it takes on the value 1, and then of course the complement of that would be the value 0, and we'll call that 1 minus p. So probability that is equal to 1 is p, therefore the probability that is equal to 0 is 1 minus p, and that covers the whole spectrum. So because it can only take on one of those two values. And this is what we talk about with heads, tails, true, false, success, failure. This is where, for example, we spin a coin and we want it to be fair because we want the probability p to be 0.5. This is what we need, for example, we talk about flippantly tossing a coin, but this is what we need for example, clinical trials. In clinical trials, which is really a euphemism for human experimentation with all the appropriate ethical considerations, in clinical trials, we very often need to, in a randomized one, decide which patient, let's say, gets treatment A, which patient gets treatment B, and figuratively speaking, we flip a coin so that in the long run, half the people will get treatment A, half the people will get treatment B. We'll come back to clinical trials later. But we don't always have to have p equals 0.5. So, for example, the issue of vaccinated, not vaccinated. Here we might be aiming at a higher percentage or prevalence, if you will, of people vaccinated. Maybe 50% is a little bit too low. So, for example, suppose that 80% of the villagers in our area should be vaccinated. So the way we model this is we say, what is the probability that at random you choose a vaccinated villager? So you go into the village and you choose a villager at random. What is the probability that they are vaccinated? So in our lingo, if you will, we want to know what is the probability that we get a 1 if we label those who are vaccinated as 1s and those who are not vaccinated as 0s. So now we want the probability of 1. So in this situation, if 80% of the villagers are vaccinated, then the probability of 1 would be 0.8. This, for example, was with Kerridge. Remember, he spun a coin 10,000 times and he got 5,067 heads. So remember, what we observed was that initially There was a lot of variability, but as time progressed, it stabilized at approximately 0.5. Now, we could go back to doing what Kerridge did, but remember, it took him years to perform this experiment. What we have a device today that we can use is a computer simulation called a quincunx. Now, the name comes from an old Roman coin, and basically what it is, quinc, of course, is from the Latin quinque, 5, and what it is this design on how to put 5 dots. And you can see on the coin, and this is like when you're rolling a die and you got your die, this is how the 5 is denoted on your die. And if you look at the quincunx, here's the picture of the quincunx, you see that these sort of triangular patterns occur all over the place. And so Galton, who invented this, called it a quincunx. So let's look at our quincunx, and first we'll start it with one row. And what we're doing here is playing with the quincunx, and once we get it to roll, you see little balls come out of the funnel up at the top, and they bounce on that peg. So there's a single peg, and the balls will bounce either to the left or to the right. And the way we've set it up is, if you look at the top left-hand corner, it says left probability 0.5. So that means that the ball will bounce to the left half the time, and half the time it'll bounce to the right. So the probability that it'll go either way is 0.5. Okay? And if you watch the bottom, let's speed it up a bit. If you watch the bottom, you see that it's roughly 50-50 how the balls fall into the wells at the bottom. So you see that after 107 balls have come out, 48 fall here. So that's 48 of the 107. And 59 of the 107 are in the right-hand bin. It's approximately 50-50. This is the quincunx. And what it's trying to do is, as I said, it's trying to emulate the tossing of a coin.